SwayamPrabha. Digital India. Educated India.
So, in the previous lecture we have seen that how the surface tension is actually defined. Here we are going to look at a second definition of surface tension. That is important, definition of surface tension. Okay. Now, if we consider it like this, that the surface tension is the interfacial tension that tries to resist any increase in interfacial area, right. So, this is like kind of a force equivalent definition, right. So, surface tension is something, okay, which tries to resist any increase in interfacial area, something that tries to resist, right, any change in interfacial area, correct. That is what it is like if we have a droplet and you want to squeeze it, right. So, surface tension is something that tries to prevent this squeezing, right. So, always the droplet example comes in handy. Say you apply some kind of a force on it, you try to squeeze it in this particular shape, okay, you will not be able to squeeze it spontaneously, right, there will be resistance that will be offered, right, because otherwise this is a stable shape. If you think about it, this is the stable shape in which droplets exist, right. You do not see elliptical shaped droplets, right, in your common life, right. Raindrops are spherical, right, when water comes out of a faucet and breaks up, it is spherical, right. So, there are many instances where the shapes are normally spherical, okay, because of the reason that spherical shapes are the most stable, and you know that the elliptical shapes, okay, they do not exist naturally. So, there must be some kind of a, if you apply a force, for example, you can squeeze a droplet, right, but at the same time you have to realize that there is something that tries to prevent the increase of this interfacial area. So, surface tension can be defined in that light also, okay. So, the work that is done on the system, not by the system, remember, on the system to increase the area of the interface okay, is given by some kind of a work term, right, and that is sigma into dA, right. So, sigma is basically the work that is done on the system, right, to produce a new surface. When you flatten this particular thing, or when you split this droplet into two droplets, you are basically creating more interfacial area, right. So, new surfaces are created, right. For that, sigma is basically that the work that is needed for doing that effort, right. So, this is like an alternative definition of surface tension. So, in that light we can write the work due to surface tension as minus sigma dA, correct. Okay. So, this is the work that is done by the system when its area is changed, okay. Work done by system, that is why the negative sign comes when its area is changed. Okay. So, the decrease in area corresponds to work done by the system, therefore, dA is basically negative, Okay, so that is the reason, right. So, it is the other way around, right. So, that is the definition. Similarly, recall that this is the basic first law definition, I am sorry. Right. Now, this work term that we have over here is basically composed of two work. It is called the PV work plus the non PV work, right. So, the PV work is basically given by d PdV, and this work is given by basically this surface tension related, right. So, this is the work that you are most familiar with, this PdV, mechanical work, okay, and like a piston moves, okay. So, that kind of a work. This is the work non PV related work, and that is surface tension is one of them, okay. We also know that dq reversible, okay, is basically equal to TdS, right, that you also know, okay, from the second law essentially. So, what we have learnt in this particular slide, in this particular page, is that surface tension's alternative definition is that something that tries to change or resist any change in interfacial area. Okay. Now, this work that is done to create new area is given by sigma dA. Now, this work is done by the system. So, when its area is changed, and since the area dA is negative, okay, because the work is done by the system, we are taking it to be a negative sign, okay, so to accommodate, to make it positive essentially. Okay. So, that is the definition that we have. Now, let us look at for reversible process. For reversible process, okay, dE is equal to TdS minus PdV minus any non PV related work, okay. G, which is the Gibbs free energy, is H minus Ts is equal to E plus PV minus Ts. dG therefore is basically given as dE plus PdV plus VdP minus TdS minus SdT, right. Okay. So, dG VdP minus TdS minus non PV related work that we have over here, coming from the definition that we have already cast over there, right. Okay. So, you can see from this expression that we have already know that these terms, these two terms over here can be cast in that particular form, right. So, we have taken into account that that thing, okay. So, that is the expression that we have, okay, that sorry, I made a mistake over here, just one second. Okay. So, it is basically SdT, okay. So, SdT has to be SdT, okay. So, you know that this term TdS, this and this, they are all given by this non PV work, right, okay, the energy, because it is minus TdS plus PdV. So, you can see all these three terms are basically accounted for by this. So, that is what the substitution we have done. We have substituted that into this expression, okay. So, that is the expression that we have. Now, for constant pressure and temperature, okay, system, what do we have? Constant pressure, constant temperature means this and this will go off, right. So, your dG will be nothing but this W non PV work, okay. Now, So, this essentially means that dg for a constant pressure, constant temperature system is the maximum non pressure volume related work, right. So, this means it is the maximum non pressure volume related work. Of course, this is in a reversible process, right. Okay. Is that clear? So, this dg therefore, is nothing but sigma dA, because you remember that was minus sigma dA. Okay. So, this gives us that sigma is nothing but dg by dA at constant T, constant P, right. So, it is a change in Gibbs free energy with respect to the area at constant temperature and constant pressure, correct. Okay. So, this is the second definition of work. So, what we have done over here, we have gone from the basic Gibbs free energy equation, substituted a few terms. We have shown that the change in Gibbs free energy for a constant temperature and constant pressure system is given by the non PV work, right, and the non PV work is nothing but, as we already know, this was minus sigma dA, correct. So, this has been substituted over here and we have got this particular definition, right. Okay. So, this actually shows that this is the alternative definition of the work, correct. So, let us now look at, before we go to the next thing, let us look at a couple of other stuff as well. We have seen all these things now. Now, let us just complete this particular section before we go on and see how surface tension and other things are applicable. Let us look at the, for a multi-component system, okay, or a system which has got compositional changes, okay, what are the requirements, right. So, for the requirements of equilibrium can be expressed in terms of different thermodynamic variables that we already know, right, for such systems. Now, let us assume it is a constant temperature and a constant pressure scenario, okay. So, the Gibbs free energy for a compositional system in terms of the Gibbs free energy is given by this particular parameter, where this k that you see over here is basically nothing but, it can be 1, 2, 3 whatever it is, right, and temperature and pressure are constant. Now, if we assume that small amounts of component A and B can be transferred across phase 1 and phase 2, okay, there are 2 phases, right. So, what will happen is that this is phase. So, K is basically nothing but the phase. So, it is basically 2 phase 2 component system, right, where the components are A and B, right. Each A and B has got phase 1, phase 2, this has also got phase 1, phase 2, right. Okay. So, that is the situation. We have so far done 2 phase, we have done 2 components, let us look at 2 phase 2 component kind of a scenario. So, assuming that there has been a transfer of components, that means some part across the 2 phases. So, for example, there is an interface you can assume. So, there is phase 1 and phase 2 and both of these comes under component A. So, the number of mole change in the second phase is equal to the corresponding loss of moles of the first phase, okay, for component A. This is for A only. Similar thing happens in the case of component B, right. So, there has been a change in phase. Now, since the system is in equilibrium, the Gibbs free energy, right, has to be equal to 0 across all the phases. So, therefore, the Gibbs free energy here has to be written across 2 components and for 2 phases, right. So, if you look at the thing over here, this is for component A, this is for component B, and this summation that you see over here, it is nothing but across all phases, correct. Okay. So, it is summed over 2 phases and it is summed over 2 components also, right. Okay. So, if you expand this particular thing out for using this particular, these 2 relationships over here, right, that there are small changes across the phases, you get this particular relationship, okay, because the change in Gibbs free energy has to be equal to 0. So, therefore, what we get out of this is basically the chemical potential of each individual component across the individual phases has to be the same, right. Okay. So, if component A is present in two phases, phase 1 and phase 2, right, two phases, okay, that means the chemical potential, okay, of phase 1 has to be the same as the chemical potential of phase 2, so long as the component is A. Similarly, for component B the same thing holds. Now, it can be a multi component system also, does not really matter. What it means is that the chemical potential across all the phases A, B, C, across all the components A, B, C, D, right, has to be the same across all the phases. Okay. It does not mean that these two are the same, just clear the, just this is not necessarily the same, right. Okay. What it essentially means that across the phase the chemical potential does not change so long the component is kept constant, got it. So, this is an important thing that will come, because we have done two phase, we have done two components, we have now seen what surface tension is. Now, we have looked into that what this means in terms of the phase space. Okay. So, these are the two things that we see over here. So, let us move into the next slide. Before we go back to the to our notes, okay, let us clear up a few other things also, because this will come in handy in the thing that we are going to cover next. Now, when we say that a system is in equilibrium, okay, it means several things, right. Equilibrium and having an unstable equilibrium, there are several ways to define it. Okay. Say for example, if you look at this particular picture over here, you see that from the parlance of mechanics, if you remember your old UG mechanics courses, you find that this is called a stable . So, this is called a stable equilibrium. Okay. Stable equilibrium means that even if you make large changes, okay, in large displacements, the system will come back to its stable state, right. You cannot make the system unstable. Whereas, a system can be an unstable in a metastable equilibrium. What does metastable equilibrium means? That it is stable over this range only, right. If the displacement is large, this will topple and go like that, right. So, it is defined as a stable equilibrium restricted to small systemic environmental changes only. It is not for large changes. That means, if this marble that is there, if you take it to a large displacement, okay, it will just fall down the hill, right. Whereas, in this case it is never going to happen. You can take it here and release it, it will come back to its equilibrium position. An unstable equilibrium means that any small displacement, no matter how small it is, it will just go into an unstable state. So, metastable equilibrium is something which is not completely stable, not completely unstable either, it is somewhere in between, and it is actually stable for small displacements, not stable for very large displacements, right. This is the mechanical equivalent, right. So, if the changes in the systemic or environmental variables exceed a certain restricted range, the metastable system becomes unstable, right. So, if there is a large change, right, not small anymore, as you can see, if it is more than this, okay, the system becomes unstable. Okay. So, that is very important because of the thing that we are going to look next. Let us look at this particular plot. This is a very standard liquid vapor evaporation dome. Now, what happens in this particular case? Okay. What you see is that this is a typical vaporization path, what you are aware from 1 and 2 it comes, right, then it enters the 2 phase zone, right, and then it enters into the vapor phase, correct. So, as you can see, the liquid is first expanded, right, then it passes through the 2 phase zone and then it is superheated, right. So, the volume the specific volume correspondingly increases. This is the traditional thing that we have all seen over here. Okay. So, the volume of the liquid can be naturally follows this particular path, right. Okay. But however, it is possible basically that the volume of the liquid can be increased via this particular path as well, this path that you see at the bottom, right. Okay. So, it is, so what happens to the liquid? It is basically compressed, right, it is basically compressed, but there is no vapor that is available. Okay. There is no vapor nucleation that has happened, because the two phase zone normally at this particular position, if you extrapolate it up to here, you will find that it is a two phase zone, right. But what we have done is that the volume of the liquid has increased, right, across the path, not compressed, actually increased the volume. Instead of going through the process 2 and 3, it has followed this particular path instead of going through that particular path. Okay. So, therefore, it is possible in the absence of vapor nucleation to basically superheat the liquid above the saturation temperature. That is what has happened. Okay. So, what we have done is that we have basically superheated the liquid above its saturation temperature without actually having any bubble formation or any vapor formation, essentially vapor nucleation, right. Okay. So, I am sorry, I made a mistake when I said that it is basically compressed, it is basically expanded, right, in this particular zone. Now, similarly, a similar path can be followed if we follow this particular trajectory, right. So, what it happens here is that the volume of the vapor is decreased now, it is decreased along this particular path 5 and 4, but instead of following 4 and 2, that particular path where it enters into the saturated regime, it can be actually made to follow the path 4 to 4 prime, okay, which means that in the absence of liquid droplet nucleation, is the reverse thing, the vapor can be subcooled below its saturation temperature, right. So, what we have done is that this is like a compression. So, we have compressed it, okay, and we have made the vapor subcooled, okay, below its saturation temperature, right, but there is no evidence of liquid formation, right. At the saturation point, you are supposed to enter the two phase zone, which is basically 2, 3, 4, right. This is the two phase zone, correct. 2, 3, 4 is the two phase zone. So, normally you follow the path 1, 2, 3, 4, 5, right, that is the path that you normally follow. What you have done over here is that you have followed 1, 2, 2 and 2 prime on the liquid side, and you have done 5, 4, 4 prime on the vapor side, right. But here you do not have any vapor, no vapor, here you do not have any liquid. So, no liquid, got it. Okay. So, this superheated liquid, which is this particular section, and subcooled vapor, which is this particular section, are both in metastable equilibrium, a typical example of a metastable equilibrium. However, the interesting question that you might ask is that what happens to 2, 3, 4 prime, can that path be followed, right. But 2 or rather 2 prime 3 4 prime, whether that path can be followed or not. This path is completely unstable, because if you recall your UG thermodynamics, okay, a simple system is at mechanically stable equilibrium if only the isothermal compressibility factor is positive. That means the volume of the system should shrink with increase in pressure, right. So, isothermal compressibility factor has to be positive for a system to be in mechanically stable state at equilibrium, right. So, if you look at this path 2, 3, 4 prime, right, that is the path 2, 3, 4 prime. What you see over here, it is completely unstable, because the isothermal compressibility factor, which is basically dV dt at constant T, because it is isothermal, right, this is greater than 0, correct. So, we can clearly see that this path is completely unstable, because as you move along this path, you get the reverse of this, that the volume of the system, okay, actually increases, okay, with increase in pressure, right. So, that is the problem that we have over here. It should actually shrink with increasing pressure, right. So, but however 2 to 2 prime is possible, 4 to 4 prime is possible. That means, if physically speaking, you can actually have supercooled liquid, superheated liquid and subcooled vapor. Those two paths are possible, right, but you cannot have the migration from 2 prime, 3, 4 prime, because that would be like unstable, right. So, this particular shaded region on the left, this is called this is the superheated liquid state, okay, and the other part here, which is the supercooled or subcooled vapor state or supersaturated vapor, whatever you call it, okay. So, that is also another metastable state. This is called the liquid spinodial, this is called the vapor spinodal, okay. So, normally when we actually do boiling later on, you will find, and in fact, in the next slide I will show, when you do actually boiling, these two zones becomes very important, right, because you can actually have a situation where you actually have superheated liquid which is which has not shown any bubble formation, and superheated vapor, right, which or subcooled vapor which has not shown any formation, okay. So, now we just look at some of the details over here, okay. Usually from classical thermodynamics point of view, right, the phase transformation occurs at equilibrium normal conditions, like it is a quasi equilibrium process, right. So, that is what you get in that particular curve, right. So, you have that straight section, right. So, if you just recall, that is what we did, right. This is the portion which is nice and steady in equilibrium, right. However, the real phase transformation, like for example boiling and other things, okay, a superheated liquid may exist. That means that liquid spinodial that we showed, okay, is not a fiction of imagination, it actually happens, right. In real phase transformation system, that is indeed a mandatory thing. Similarly, in the condensation process, that is the other way around, right, the vapor is usually subcooled, right, or supercooled, whatever you call it, either way, below the equilibrium normal temperature. It is a subcooled, this is a very cold vapor, right, even though it has not undergone the condensation, right, okay. But, and we will come to that later, the superheat limit is the maximum temperature that a liquid can be heated before it homogeneously nucleates. So, there is a threshold also, right. Beyond this threshold, if you do, the liquid after that will homogeneously nucleate, start showing vapor pockets, right. So, that is that there is a maximum temperature up to which you can heat it, right, beyond the saturation point, okay. So, as I said, we already established that though we say that liquid vapor transition, right, the phase change is a quasi equilibrium process, it happens along that straight line and things like that. In reality, we saw that the vapor is the liquid is actually superheated, okay, and it can be superheated to a certain temperature before you actually start to see the nucleation, means bubble formation or vapor formation, right. So, people have calculated it, okay, the degree of superheat actually is not a small quantity, it can be from less than a 1 to a few hundred degrees, right. So, that means this is the level of superheat and this is the saturation temperature. So, basically you can heat a liquid, okay, to a point much above, you know, its saturation temperature, right, without having any bubbles. So, if you look at this table, once again this is from Fagri's, Amir Fagri's book, okay, which is a prescribed textbook for this particular course. Okay. You can see that there are, for example, different pure liquids at atmospheric pressure, data compiled by Professor Tom Avedisian, okay, from a 1986 work. So, if you look at N-pentane, for example, its saturation temperature is 309. Okay. Now, the degree of superheat, and these superheats are calculated using van der Waals and different other equations of state. We are going to go into those details later, but assuming that whatever it is, there is a superheat level. So, one is 405, one is 431. right. So, that means there is almost 100 to close to 120 degrees Celsius, okay, that you can heat a liquid before it starts to boil. Okay. Similarly, for N-heptane you see a similar thing, N-octane you see a several thing, methanol for example also shows a similar thing, ethanol also shows a similar thing, and water is really high. If you look at it, is almost close to 200 degrees, okay, 552 and 596, right. So, it is very high. Okay. So, these values are significantly higher than their respective boiling points. If you look at a boiling point of water under atmospheric pressure is 100 degrees Celsius, right, but here you are getting 552 Kelvin. Okay, 552 Kelvin is almost 300 degrees Celsius, right, or close to that, give or take. Okay. So, they can undergo, which proves that they can undergo substantial superheating, okay, even beyond their normal boiling point. And in fact, in the case of multi-component droplets, okay, when you actually have boiling inside a droplet, we actually do see such things. Okay. So, this can be all encompassed in a kind of a correlation which is given by this particular form. Okay. So, this is like a correlation which says that how to calculate the degree of superheat basically when you know what is your saturation temperature and other things. Okay. Clear? So, once we know, so we know a few things now, that there is something called a liquid spinodal, there is something called a vapor spinodal, liquid can be superheated, vapor can be subcooled. So, there is a degree of superheat that is involved before you see any vapor or bubbles appearing in the system. This is very important for the boiling community, right, and this degree of superheat is not just 1 or 2 degrees, okay, it can be hundreds of degrees essentially. It can be very small, it can be very large, as has been proven by this particular table over here, like the work of Avedisian et al. So, I think this is a very important part that you get, which you did not get in your previous thermodynamics book. You always thought that the phase transformation happens across a straight line, correct. So, it is a nice like this essentially, right. So, it happens across this particular line. So, but phase transformation does not necessarily happen in that particular way. Okay. You have a system which is quite a bit deviated from its equilibrium. So, it is in a metastable equilibrium state, right, before it starts to show any vapor formation, or if you look at the reverse process which is condensation, whether it shows any condensation process or not. Okay. So, just looking at this previous slide, okay, you can see that we have put a lot of markers over here. Only the path represented by 2 prime, 3, 4 prime is unstable. 2 to 2 prime, 4 to 4 prime, these are stable or metastable paths. That is something that you should keep in mind, because the next thing that we are going to do is a little bit of a boiling, I mean little bit of a vapor formation, how that actually happens. Okay. So, let us look at this, I mean let us go back to our journal once again, and so before we go, so we end lecture 5 over here, okay, under this note. The next lecture that we are going to start will be on micro scale vapor bubbles and liquid droplets, how they form. Now that we know a little bit about these boiling curves, we know a little bit about the interface, we know a little bit about surface tension, right. We know how surface tension can have multiple definitions. So, in the next lecture we are going to look at this particular problem. Okay. So, meet you in the next lecture.